Welcome to the video on Bode plots. Bode plots are a way of displaying frequency response data. So we're going to explain how the frequency response of a system can be read from a Bode plot, and also how to create a Bode plot given a system's transfer function. So Bode diagrams, again, are a way of plotting the frequency response function. We'll often write that as g of j omega. So g is our transfer function, and we evaluate that at s equals j omega. There are two halves. There's a magnitude plot, which plots the magnitude of g of j omega in decibels. Okay, so decibels, actually, you take the magnitude and you multiply. You take the log of the magnitude with the base 10 and multiply by 20. That is converting it to decibels. And I will often write decibels with a double magnitude, double norm, double absolute value signs like this. And you plot it versus logarithmic frequency. In other words, instead of plotting a straight scale on the frequency axis, you use log scale. All right. Now, similarly, for the phase plot, you use a logarithmic frequency scale. That makes sense. But we just plot the phase angle of g of j omega in degrees. Okay. So in order to plot the Bode diagram, you need to calculate the magnitude and phase of each transfer function. Let's take this as an example. If we want to calculate magnitude, you remember the best way to do it is to take the magnitude of the numerator and divide by the magnitude of the denominator. Okay. Now an easy way to write this, I'm going to rewrite the bottom so that I have my real and imaginary parts all consolidated. So the real part of the top is 1 plus j times omega. And on the bottom, there'll be a real part resulting from this j omega times j omega, and that's going to be a minus omega squared, okay? And then there'll be a plus j times 10 omega. So the real part of the top is 1, and omega is the imaginary part, and negative omega squared is the real part of the bottom, and 10 omega is the imaginary part. So the magnitude of the resulting transfer function, we add the squares of the real and imaginary parts of the top and the squares of the real and imaginary parts of the bottom. Okay, and that is the magnitude. You'll remember for the phase, the easiest way is the phase of the top minus the phase of the bottom. Okay, so if we think about the angle of the top, okay, on the real and imaginary axis, that's going to start at 1, and it will travel upwards with omega. Okay, so that's going to, we're going to take essentially the arctangent of the imaginary over the real part. So, oops. Inverse tangent of omega divided by 1. And then we're going to subtract the phase of the bottom. Now, the bottom starts off, it has a increasing positive component here, but it's actually going to be negative and then eventually go up like this. So that one will look more like this. Okay, so it'll start at a minus 90, looks like, because this term initially dominates, and then it will move to the left. But it's basically the same idea. What's the imaginary part here? It's going to be 10 omega divided by the real part, which is minus omega squared. And we'll have to make sure that that is between 90 and 180. Okay. So if you wanted to plot this out, you take these two functions that we have come up with, and you create a list of values like this. At many different frequencies, you would try to plot them on these graphs. So you would start, and then you would find the magnitude. You'd convert that into decibels. So looks like we start here around a 0 decibel, just above, at a frequency of 0.1. At this point, we are almost minus 20. Okay. Here's this one at minus 5. So you just plot a few points on here. Oops. And let's see here. Here's a 10, minus 22. And finally, let's go ahead here with a minus 40. Okay. And what you would do is you would see this works out something like this. All right. Similarly, for the phase plot, we would find out this starts actually around almost a minus 90 degrees. Okay, at this frequency, it actually is minus 90 at 0 degrees, and it's going to rise up, peaking around this area. And do something like that. Okay. So in general, we have a transfer function that looks like this formula. We have a ratio of polynomials. And what we can do with that, but the important thing is that we can split it up into a gain and zeros and a gain and poles. Okay. In practice, we can always calculate the magnitude this way. Okay. The magnitude of j omega is the magnitude of that fraction then, and you can split it up and multiply the magnitude of each pole times the magnitude of each zero, and then also times the magnitude of the rest of the thing. If we take 20 times the log 10 of that, we'll be able to split up these individually. Okay. Also need to add here 20 log 10 of v over a. Okay. The main point here is that knowing the individual poles and individual zeros, how they contribute to the Bode plot, I could actually just plot them out individually and then add their graphs graphically. Okay. It's the same for phase, or at least very similar. For phase, the angle of g of j omega is the angle of the zeros minus the angle of each pole. Okay. All right. So taking this example, right, I would first have to factor this function into zeros and poles. So I would pull a 3 out of the top, okay, and actually a 3s. What would be left would be s plus 3, s plus 1. Okay, you say, now that's easy to find for this one. How would I do that for a more difficult one that wouldn't be so easy to factor? Well, for a more difficult one, I would recommend using MATLAB to find the roots of the numerator and the denominator. On the bottom, I'm going to pull out a number 2, and what would be We could also factor this into an s plus 5 times s plus 4 times s plus 2. Okay. And so then eventually we would get to be able to find the magnitude and decibels of g of j omega. That would be 20 times log 10 of this gain here. Okay. I'd have to add 20 log 10 of j omega plus 3. Okay, I take the magnitude of that. Plus 20 log 10 of j omega plus 1. Okay. Then I would wind up subtracting the 2 I've already taken care of here, but 20 log 10 of j omega plus 5 minus 20 log 10 of j omega plus 4, and finally minus 20 log 10 of j omega plus 2, all their magnitudes. Okay. So the main point here is that I could find these the magnitudes of these poles separately. Okay. And finding them separately, I could then add them together graphically. I'll show you again what I mean. Oops. And phase, okay. Angle of G, okay, at j omega. That's going to be, actually we do have to take the angle of this 3/2 portion, but that's basically going to be 0. Okay. If it was negative, now it would be 180. Keep that in mind. Plus the angle of that s on top will be a j omega. Okay. Plus the angle of j omega plus 3. Okay. Plus I've got one more 0, the angle of j omega plus 1. Okay. So much for the zeros. Now I'm going to go to the poles. My first pole, angle of j omega plus 5. Okay. Minus the angle of j omega plus 4. Minus the angle of j omega plus 2. Okay. So again, you see I'm able, based on splitting up my transfer function into a gain, zeros, and poles, I'm able to look at the effects separately, individually, and just add them up for my final Bode plot. So this is very important. Let's keep moving. Let's take a look at how each of these poles, zeros, and gains, how they affect the Bode plot. What are they going to do? For starters, let's take a real pole, okay, with a static gain of 1. You see that the static gain, take s to 0, 1 over 1 is 1, okay. So you may have to divide some of the poles that we've done by, you may have to reorder them, restructure them in order to get them in this form, but it can be done, okay. So, and we make the stipulation tau is greater than 0, that means it's going to be a stable pole. Alright, if you calculate out the magnitude, it's going to start out at a magnitude of low frequencies, j omega will be 0. It should start at 0 decibels, which is the same as 1. Okay, and about the frequency of 1 over tau, you'll see that we start to move here, and we move down by about 3 decibels. Okay, what's 3 decibels? 3 decibels is actually that's equal to 1 divided by the square root of 2. Okay, because you see, once we put in, for s, we put in a j omega, and omega is 1 over tau, we'll have 1 for the imaginary part, 1 for the real part on the bottom. Okay, and so that'll give us this. That's useful because it's like about the point where the graph would be about half of the power. Okay, when you square this, you get a half. So we often talk about the 3 dB down point, and we call this the cutoff frequency. For the same reason, when you look at that bottom portion, all right, the angle of the bottom portion, if you would plot it out, where both are equal, you have an angle here of 45 degrees, okay, on the bottom, and therefore the phase of the entire transfer function is minus 45 degrees. Okay, and the explicit formulas for calculating this are right here. The magnitude is 1 over tau squared omega squared plus 1, and the formula for the angle is going to be arctangent of tau omega divided by 1, because the real part on the bottom is 1. Okay. So, but what you'll see, again, just in general, a pole will have a nice flat response towards 0, like this. And as you go towards infinity, what you see here is this is going to be a fall-off rate of minus 20 decibels per decade. Okay, and what is a decade? A decade means multiplying the frequency by 10. Okay, so if you look at the magnitude at this point versus the magnitude at this point, you'll see that it's actually going off it's lower by 20 decibels. Okay, if we went another factor of 10 higher, okay, so 1,000 over t would be the frequency, you'd see that this would be at negative 60. Okay. And the same thing you find out for the phase plot. At the cutoff frequency, 1 over tau, we have a frequency of minus 45 degrees. And about a decade before and a decade after, we have about 45 degrees of phase. So it's almost like you could approximate this by drawing something like this. And often we do that. Yeah. And this one you can almost approximate by drawing all the way to flat, all the way to the cutoff frequency, and then down at that slope of minus 20 dB per decade. And then you just smooth out the graphs. All right, that was a first order pole. Let's now talk about a first order real zero. Okay, so the same thing, and let's say that tau again is equal to 0. That puts the 0 in the left half plane. Sometimes we'll call that a stable 0, even though zeros don't have any impact on stability. It's just to say that 0 is in the left half plane. And it basically, if you'll see, it basically flips the graphs over the 0 dB magnitude line and 0 degree phase line. Okay, so if you compute the magnitude, you see the magnitude is actually just the magnitude of the top. Okay, so because the magnitude of the bottom is always 1, so we take tau j omega, the imaginary part is tau omega, so we square that, and 1 squared is 1. And taking the angle, you can imagine, we've plotted this before, but the real versus the imaginary part, we have a constant real part of 1, and the imaginary part of j omega just goes straight up. And so you'll see this angle here starts at 0 here, and as omega increases, it goes to 90 degrees. Okay. So a few things that are basically fall out of this. When you have a frequency of 1 over tau here, when omega equals 1 over tau, what you'll see is that we're at this point on the graph. This is again what we call, sometimes we'll call this the cutoff frequency, or the break frequency and cutoff frequency, and you'll see that it occurs at 3 decibels. Okay. You'll also notice that in this case it's now a positive 20 decibels per decade slope as you go to very high frequencies, and it'll stay like that. Okay. Flat on the left, a slope of 20 decibels per decade on the right, and at the cutoff frequency we have 3 decibels larger. So the pole was down by 3 dB, the zero will be up by 3 dB. And same thing for the phase. We start at 0, go to 90, and we hit 45 in the middle, because that's going to be this point exactly here where the real and the imaginary parts are going to be equal. Okay. What if we have an integrator, or in other words a pole at 0? Well, the frequency response is 1 over j omega. What's the magnitude of 1? That's 1. What's the magnitude of omega, or sorry, yeah, of j omega? It's just omega. So the magnitude will just be a 1 over omega. Okay. When you take a log of that, it just winds up being a straight slope. Okay. So just imagine when I put in here 10, I have a magnitude of 1/10, okay, or -1. When I put in 100, I have 10 to the 2, or 10 to the -2, so the log is -2, and I'm going to get -40. And so this will basically just keep going down, and it's just that slope of -20 decibels per decade. Okay. For the magnitude, you can see the magnitude of the top is always going to be 0. The magnitude of the bottom, if we plot it out, it's just a imaginary portion, right, that keeps going up. It's always 90. So 0 minus 90 is negative 90 degrees. So these are quite simple. You just lower the phase everywhere by 90 degrees, and the slope of the line is -20 dB per decade. Now, where do I draw this? Okay, how do I know where to position this up and down? Okay, the easiest way is to take this frequency of 1 radian per second, okay, and make sure that your graph goes through that at 0 dB. Okay, so that will anchor the plot, and then you draw up from there and down from there at that slope. So that was a pole at the origin. How about a 0 at the origin? Okay, well, it's going to be exactly flipped over that 1 dB point. So again, when this is 1, when omega is 1, the magnitude will be 1. 1 is 0 decibels. So we need to make sure that we go through, at 1 radians per second, we go through 0 decibels. The phase of a purely imaginary number is always 90 degrees. And the slope is 20 decibels per decade. Okay. So those are quite simple. All right, to summarize the first order, for a pole, we have a break frequency at 1 over tau, okay? And the same thing for a 0, we have a break frequency at 1 over tau. So the pole will break downward, the 0 will break upward on the magnitude plot, okay? So we'll often approximate this as a straight line under the pole, and then that slope of -20 dB per decade after that. Okay. And the same thing for the 0, just in the flipped over the 0 dB axis. For the phase plot approximation, okay, we go through minus 45 degrees at that break frequency. Okay, so you draw out minus 45. You make sure you go through there. This would be at omega b. And 1 decade above, we go flat at 0. 1 decade below, we go flat. And so this will be 0, and this will be minus 90. So if you notice, our first order pole had a wound up at minus 90 and so did the integrator. You can think of a pole as always subtracting 90 degrees of phase, and a 0 is always adding 90 degrees of phase. Okay, high frequencies. So the same thing for the zeros. We go 0 dB until the break frequency, and then we go up at that slope of 20 dB per decade. Okay. All right. So when you see a Bode diagram, because you know that the phase, for example, every 0 will add 90 degrees, every pole will subtract 90 degrees, you should be able to look at the phase plot and know, do I have more zeros or more poles? Okay, and how many more? So if the plot winds up at minus 90, you've got at least one pole more than your zeros. Okay, and the same thing from the magnitude. If you look at the far right side of the graph, okay, when you have a constant slope, you should be able to tell that slope from that slope of the line what the order of the system is. You know, do I have one more pole than the zeros or two more poles than zero? If I had 2 poles more than the number of zeros, my fall off rate will be minus 40 because they'll cancel each other up to a point, and if I had 2 more, each of them would give me minus 20 dB per decade. Since they add together, the slopes add together, and it would be minus 40 dB per decade. Okay. All right. So a little more complicated. Let's go ahead and try a second order set of complex poles. Okay. So we're going to want to split these up into omega n, the natural frequency, and zeta. So writing them this way gives us a magnitude, steady state gain of 1. Okay. So 0 decibels, and at low frequencies, okay, these two terms will drop out, and that's why we're flat at 0, just like the first order system. Okay. So but since we have an s squared, that'll be a j omega squared, and that's what leads to this negative term here. Okay. And I've divided through to make this simple. I divided through by omega n squared on top and bottom. So my imaginary part is always 2 zeta omega divided by omega n, and my real part is always this part. Okay. So the formulas are pretty easy to get. All right. So what does this look like? Well, around this frequency of omega n here, okay, we see some interesting things happen, right? The real part of this actually goes to 0. And so that means since the real part goes to 0, we're looking at tangent inverse of some non-zero part here, right? That'll be just 2 zeta, but the bottom will be 0. Okay. So the bottom will have a phase of 90 degrees. Since we'll subtract that, we'll be at negative 90. The top will just be purely real and have a phase of 0. So at omega n, you always go through minus 90 degrees for a second order system. That's going to be very important. Now, you'll see that having this go to 0 actually can give you a peak in the Bode plot. Okay, so we may actually go up before going down. And it actually is going to happen just before the omega n. Okay. All right. Now the slope on the right side here, instead of minus 20 dB per decade, it's actually going to be minus 40 decibels per decade. Okay. And you'll see that here's 10 omega n, and here's 100. Okay. Minus 40, minus 80. It's lower by 40 decibels. Okay. For 0, okay, if we were to write the 0 like this, where we have, essentially just the inverse, it turns out that just like for a first order 0, you just get a flip of the graph over the 0 decibel line and over the 0 degree phase line. Okay, and the formulas are also easy to compute because here we had 1 over, and here we just flip that over 1. Same thing here, we can just do a minus the formula we had before. Okay, oops, and we already had a minus because it was the phase at the bottom. We have that. Okay. Now for this case, at a frequency of omega n here, we're going to have a plus 90 degree phase. Okay, it's going to be very important for finding for any second order poles or zeros, knowing that at omega n is where the phase goes through minus 90 or plus 90 for zeros. Okay, and again, keep in mind the slope as you go to very high frequencies will always be plus 40 dB per decade for a pair of complex zeros, because there are 2 zeros, each one gives you 20 dB per decade. So together they give you 40 dB per decade. Okay. So to summarize, second order complex poles with zeta between 0 and 1, we have a break frequency near the natural frequency. Okay. Now to approximate the magnitude plot, we start out flat at low frequencies at 0 decibels. Okay. Around that break frequency of the natural frequency, we may have a peak, okay, which we can calculate using this. Okay. And then after that, we want to go down here at minus 40 dB. Okay. So the easiest way to draw this is to put in where you have that, 0 to there, and minus 40, and then maybe work that in later, okay, by calculating it out on the graph. And I want to make a point that that maximum does not actually occur at omega n, but it occurs at 1 minus 2 zeta squared. Okay. All right. For the phase, actually, it's best to use a little bit of an approximation here. So 1 over 5 to the zeta power times omega n. Okay, and 5 to the zeta power times omega n. Okay, so you can calculate what those two frequencies are. Okay, and if this is omega n, right, we draw here at minus 90 degrees. We want to go through that plot, and then you calculate this one to be 5 omega n, 5 to the zeta power, and this is going to be 0.2 or 1 over 5 to the zeta power omega n. Flat from there, sharp to there, like that. And for the zeros, these are flipped over. The 0 dB and 0 degrees phase. This will be a minus 180. That's really bad, sorry. We're going to wind up here at a minus 180 degrees. Okay, so it's like each pole of this, the second order system, each of those poles will give you a minus 90 degrees of total phase lag. And so together they give you a minus 180 degrees. Okay. So similarly, the second order zeros would give you 180 degrees of phase lead. They'll add 180 degrees of phase as they move across the frequency. Okay. So let's take a closer look at a second order pole. The frequency response function, we plug in j omega for the s's. Okay. So if you'll notice here, if I divide through by omega n, top goes to 1. This j omega squared becomes minus omega squared divided by omega n squared. And same thing, 2 zeta omega n times j omega divided by omega n squared, and you get this. Okay. So here's the magnitude, here's the phase. Okay. If we were to take the magnitude and take the derivative and set the derivative equal to 0 and solve for the frequency omega that makes that a maximum, we would find this. Okay. And if we were to plug in that omega r, so omega here would be omega r, right? What you will find out is that you'll have a maximum of this. Okay. And then of course when we plug in omega n, okay, not omega r but omega n, this real part down here, here's the imaginary part. Actually, just strictly without the j is the imaginary component. Okay. And here's the real part. The real part goes to 0 when you have omega n, or at omega n. Okay, so the imaginary part is 2 zeta omega divided by omega n. That will be non-zero at omega n. And this one will be 0, and so the phase will be minus 90 degrees. Okay. All right. So let's take a look at what different values of zeta will do to the system. Okay. For a very small zeta, if you take a look here, very small zeta, the bottom here will get very small. That will make the result, the maximum value, very large. Okay. And similarly, very large values will make that maximum disappear. In fact, if you take a look, omega r, if I have a zeta greater than square root of 2, or greater than 1 over square root of 2, I should say, or about 0.7, this won't be a real number anymore. Okay, so you will not see any peak at all. That's for a zeta of greater than about 0.707, 1 over the square root of 2. Okay, there's no peak visible. All right, so this is zeta increasing from nearly 0 for the top plot, high peak for low zeta, and no peak for zeta greater than this. Okay, and you'll also see this is the direction of zeta increasing. So for very small zeta, we have a very sharp phase plot, very sharp peak, very sharp and steep phase plot. And for very large zeta, okay, you see it's a very, very smooth plot. Okay. For the last one that's plotted, you can see essentially we have this straight line through here, which is how we approximate it. For the last one, we would draw the approximation like this for the phase plot, but you can see for smaller values of zeta, we need to do much more steep. And that's why for the approximation, we have it as a function of zeta. Okay, right here. That's the one frequency, that's the other frequency where you draw your plots. Okay. So what you'll see is that a higher damping ratio, a higher zeta, will always smooth out the magnitude plot, and it will smooth out the phase plot. Okay. But keep in mind, what's the same with all of these is that they start at 0 and they go to minus 180 degrees because they're all second order systems. And they all start here at 0 and they all fall off with this same rate. What's the rate of fall off? Well, here's 10, here's 1, okay? All minus 40 dB per decade. Okay. Just a few more things before this video closes. We have 3 different characteristic frequencies. The natural frequency, the damped natural frequency, that was a frequency that we had for timed response, okay? And it was equal to omega n times 1 minus zeta squared, okay? And now we have a third, which is a resonant or a peak frequency, omega n times 1 minus 2 zeta squared, okay? So the lowest will be omega r, then omega d, and finally omega n. Okay, so they will not be equal. When the damping ratio is greater than 0.707, okay, it's impossible to have a real frequency here. What that means is that there will be no peak in the Bode magnitude plot. Okay, so for small zeta we get this peak around omega n, a resonance. Okay, for large zeta there is no peak visible. Okay, if you have very sharp eyes, you might notice that the magnitude, the peak actually moves to the left, okay, as zeta increases. All right. Do not confuse not having a peak in the Bode magnitude plot with having an overdamped system. Okay. All of these systems were for zeta less than 1. Okay. All of these systems will display overshoot in their step responses. Okay, there will be more overshoot for the smaller zeta. Okay, but all will exhibit overshoot. Okay, between 0.7 and 1, you still have overshoot. Okay, you still have an underdamped system. The only difference is you will not have a resonant effect. Okay. You will always have the magnitude will always be decreasing as you increase frequency, just like a first order system. All right. So as it approaches 0, as you get less and less damping, omega r converges to omega n, as would omega d. Okay. And g of j omega max also increases. And the phase transition from 0 degrees to 180 degrees becomes sharper. Okay, so that's a few more things to keep in mind about second order poles. Okay, thank you very much for watching.